Video and so hi everyone. We are going to start today's session. That is, today's session is on Cox Proportional Hazard analysis. So let's begin this session, and there are a few questions in the beginning of the session. So all of you are requested to type in the chat box. So let's begin this session with a simple mathematics first. So now you can see, what can you see in this screen? There is a girl here and there is a boy. And we have measured something, any outcome which we have not specified. And the start time, the measurement was 0. And in boy, it is 2. And if I need to maintain the same amount of difference between male and female at each time point, so there are various time points like start time, which we can take as 0 time. Then there is a 3 months, 6 months, 9 months, and 12 months. So if I have to maintain the same difference between the measurement of a boy and a girl, what value should I type here at 3 months? All of you, please type in the chat box. What value? So, okay, Shibaji has written 3.5, 5.5. So you are well ahead in answering. Manoj is writing 3.5. Dhruv is also writing 3.5. So you are right, it is 3.5. And similarly, if I have to see for 6 months, then again, if I want to maintain the same difference, it is the difference between these two. And at 9 months, it will be 5.8. And at 12 months, it is the 6.4. So this same concept we have done in the ordinal logistic regression. That's why maybe those of you who have done the session on ordinal logistic regression, because there also there is a assumption, which is the assumption of proportional odds. And similar of that assumption here in the Cox Proportional Hazard. So that's why this initial exercise is there. Now coming to the second exercise. Now in this case, I need to maintain the same ratio. So in the previous example, it was the difference. Whereas in this example, if I want to maintain the same ratio between male and female at each time point, then how can I do it? So what should be my answer in this case at 3 months? So 3, right? At 6 months, Dhruv is writing 3, Manoj 7, Sinduri 7, right? Neha also 7, Rutuja, Anjana, Jennifer, Manoj, all 7. At 9 months, what should I do? So Shivaji is writing 7.6, Sinduri 7.6, Neha 7.6. Yes, you are right. It is 7.6, but we have written 7.4. And here it is 8.8. So except for this 0.2 difference, it is almost the same ratio is there in between these girl and a boy. Now consider a hypothetical study where I want to see the effect of gender on the second heart attack of MI, because we have been doing the life table analysis, the Kaplan-Meier analysis on this data set only, where the event which we have described, that is the second attack of the MI, and the inclusion criteria is all those individuals who had the first attack of MI, we have taken those individuals. So if I want to see like whether the survival probability is different, or maybe the hazard, what is the hazard ratio? So now I will define this concept of hazard maybe later in the later part. But if I want to see that, so something known as the hazard ratio. So it is very much similar to the odds ratio, which we have learned in the logistic regression, except that it is a time dependent. In logistic regression, you only take the outcome. Whereas we have seen that in all survival analysis, we have got two dependent variable, and the two dependent variable, the first one is the event, whether the event has happened or not, and the second event is the time taken to get that event, or maybe the time taken for censoring. And we have discussed regarding the censoring, the type of censoring, and what is the importance of censoring. And we have also seen that why this survival, why this survival analysis originated? Because if you calculate, like we discussed, if you calculate an incident rate or an incident rate density, there it does not take into account of all those people who are missed in the follow-up or who have withdrawn from the study, and the time is available with you, that much time. So that's how there was a invention of the survival analysis, where it takes that follow-up time or the time for which the study participant was there in the study, it takes account of that time also. So in this case, if I write here, like you can see at start, the first in the female, the ratio, the hazard is 1 and 1.2. So hazard ratio is 1.2. If I take the female as a reference and male, I want to describe the hazard ratio in male, then it will be 1.2. So what is the hazard ratio here at 3 months? Like if it is in male, it is 2.6. And if it is in female, it is 2.2. Then what should be the hazard ratio? All of you, please type in the chat box. So Rizwan is writing 0.4. So you have to divide this 2.6 divided by 2.2, because 1.2 will be, if you want to take, then in that case, I want to, so it is 1.18. Okay, right? You are also right, Rizwana. The only thing is that you did 1 by 1.2, whereas I am just telling it is in the term of more than 1. Again, you know that the odds ratio, the value entirely depends like what is the reference. So if in your case, the answer which you did, that was the odds ratio in female when you have taken male as a reference. So yes, it was somewhat 1 point. What you people wrote, let me just see. So Dhruv is writing, how have we come up with hazard? Please repeat. So I will tell you right now only hazard. Remember hazard we have defined like the failure. In the first class, we defined that what is a hazard. So hazard is a failure or the event which you describe. Like if I describe the what is like after what time there will be the second heart attack or second MI in all those individuals. So occurrence of second MI, that is the, in that case, we can say the people who have survived this occurrence of second heart attack, that is the survival probability. And the event which we describe, that is actually a hazard. Event is positive. Like in many cases, we see that remission in cancer or the ambulation in knee replacement. Then in that case, although that event is positive, but we, by definition, we call that as a hazard. And those of the individual who could not be like ambulated after that time, although that is a negative thing, but we will call that as a survival. So by definition, that failure is known as the hazard. And at each time point, we calculate the speed of occurrence of that outcome in this case. So Dhruv is writing, if 2 out of 10 patients had repeated MI, will 0.8 will be survival. So if 2 out of 10 patients had a repeat MI at 3 months, then 0.2 will be hazard and 0.8 will be survival. So if, like by definition, I said that event which you have described, that is the hazard. So if MI will be, so if it is 2 by 10, so initial at end of the 3 months, if there is no loss to follow, because you are only telling me the like incidence of the case, you have not told me the censored. So in that case, both the cases that must be at the same point of time. So 2 out of 10 patients, so remaining patients will be, in this case, it will be 0.2 and 0.8 will be survival. Yes, because like there is no censored or no loss to follow up. So you are right, survival will be the people who survived after that time. Survival, we only say, that's why we call it like, cumulative survival. So if I take at 3 months, so that 3 months is the delta T, the small time period. So I may say that probability of survival in these things is 0.8 after 3 months. because once that person has crossed 3 months, then only you will say that that person has survived. Okay, so but don't get confused, because hazard rate is not the exactly opposite of survival. This is the probability, but the formula of hazard rate, it is a rate, whereas the survival is a probability. The only concept which I want to say, that we will see it later, it is coming in the later part, that this probability is divided by delta time t, and that's why we call it as a hazard, because probability cannot go beyond 1. So the range of probability is between 0 to 1, but hazard can go up till infinity. And that's why hazard is a rate, it's not a probability. And the formula is a little bit, it is taking like calculus part. It's a mathematical formula which converts the survival probability into the hazard. But it's not the opposite of hazard. Don't think that, 0.2 is the probability of that hazard, but it is not the hazard rate. For hazard rate, it's the different formula, and you cannot calculate it manually, because I said you need to know the concept of calculus. That's why hazard rate is calculated by the software. It is not something like, by putting that 1 minus, we can do it. So that's why. And Dhruv, maybe I am coming to this concept later, just after a few slides. Until the time, you just think that this is very much like a odds ratio. The difference is like there is a time factor also in this. So in this case, you can see that at 9 months, so if you take the proportion, so what will be the 4.2 by 3.5? What will be the value? So if I see the chat box, I think none have written till yet. So if I let me do it. So I'll open my calculator. So 1.2. Okay, you people have written. So it is 1.2. Then what will be the 5.5 by 4.6? It is again 1.2. So you can say that it is constant across each time point. That means this ratio, which is there at the start, this is constant at each time point. So in the previous example, we can say that the effect of gender on second heart attack is same across each time point. Can I say that if the hazard ratio, or even if you don't understand the hazard ratio for now, the odds ratio, can I say that since it is constant 1.2, although it is changing, the hazard in both the categories is changing, but it is keeping the same ratio. So can I say that it has got the same hazard ratio at each point of time? Although the hazard in both the categories is changing individually, but somehow the ratio is same. So we can say in the example that the effect on gender on second heart attack is same across each time point. Now consider this new result in comparison to the previous. So the upper part of the slide, you can see this was the previous example, and this is the new example. So now consider this result with comparison to the previous. So now what will be the value of 2.5 divided by 2.2? So please type in the chat box the value of 2.5 divided by 2.2. So it is 1.13. Okay, I'm writing whatever you people are saying. And then what will be the 3.5 by 3.1 answer? So all of you please calculate it. 3.5, it is 1.13. 3.9 by 3.5, what will be that? 1.12. And 5.2 by 4.6. What will be the answer? 1.14. So there is a range. You can see it is from 1.11 to 1.14. It is not exactly same. So here we can see that in this case also, the hazard in both the category is changing, but it is keeping. Then what should I give the statement? Should I write like this? Now, can we say that the effect of gender on second heart attack is nearly same across various time points? Can I say that? Because I can say that there was a difference, like maybe it is 1.11, 1.12, 1.13, etc. So can I say that it is nearly same across each time point? So yes, all of you agree. Now, if this is the changing hazard at each point of time, so instead of like 3.1, you can see here, if you compare it with the upper example, and then if you see it is 3.9, instead of 3.9, it is 0.9 here. Then will this ratio 0.9 and 3.9 now, or this 1.8 and 3.1? Now tell me, what is the hazard ratio at 6 month, 9 month, and 12 month? If I'm taking female as a reference. So in this case, I'm taking female as a reference. So if I see the chat, so still I have not received any answer, waiting for your answer. So 2.06, 9 month, 0.25, 0.58, 0.6. So you can see here that it is not 1.12. So what can you say? So can you say in this case that the effect of gender on second attack of MI is nearly same across all type point? What is your answer? Yes or no? So yes. So most of you have answered no. So now what will be my statement? That gender had a different effect on heart attack of MI across various time points. So do you agree with this statement? Like gender has a different effect. It is not the same impact at each time point because this is changing. This proportion is changing or the ratio is changing. So this concept, this you have understood. Now we'll again come back to this concept when this is known as the proportional hazard concept. The concept which you have learned, like even if the individual hazard is changing in both the group, but the ratio, overall hazard ratio is nearly same at each time point. This is known as the proportional hazard assumption. And this is one of the assumptions which needs to be met before we apply the Cox Proportional Hazard. Again, we'll come to this concept. So now we formally begin our session on survival analysis. So we all know that rates are not, because in day 1 and day 2 also we discussed that why can't we take incident rate, like we discussed that, total incidence divided by the person time. We can take that for a calculation of this outcome, which is the incident rate. But we don't take why there was a need of this survival analysis. So the first thing which we read, that is only applicable when that rate is constant for that entire period. And in any study, if you do a RCT or any prospective study, the rates keep on changing. It is not same. Like for example, if a person has got a high heart surgery, so the rate of death, that is very high initially. But when the time passes, the rate goes down. And then again, it rises again. So you cannot say that the risk of death will be same throughout the post-operative period or throughout his or her life. Similarly, if you have done a surgery for a tumor or a breast, let's suppose a breast cancer. So the recurrence rate of the tumor following the diagnosis, that is very different. In the initial time, that recurrence is low because just now the patient has undergone the various type of therapy, like chemotherapy, maybe surgery, maybe radiotherapy, but the recurrence rate may rise in the later part. So we can say that the hazard, this risk, whatever event we describe, that is not same. In case of a copper T, will you say that the risk of expulsion of copper T will be same for 5 years? What is your opinion? If you do a survival analysis, you will see that this risk is most common in the early part, maybe first 6 months, maybe first 1 year. Those of the people who survived after this 1 year, there is a very less, ultimately there will be a day, if you can follow up that woman for 20 years, definitely she will get the copper T removed. But the rate will not be the same throughout her reproductive period. It is definitely high in the early, when it is just she's getting adjusted for that copper T. So you all agree that rate is not constant in any period. And that's how we always define this instantaneous hazard or instantaneous rate, which is the rate at that particular point of time. And it is changing. So that's why it is always expressed as a function of T. Whenever we write H as a function of T, that says that it is an instantaneous rate at time T, which keeps on changing. So that risk is not same all the time. So now, why this Cox proportional hazard? Because by this name also, you will see the name of this is the Cox proportional hazard. So this proportional concept we have seen in the initial part when we were doing that question regarding the maintaining of that ratio. So in this case, like in Kaplan-Meier, what have you seen? So in Kaplan-Meier, we only see like what is the median survival time. And that we have seen that why do we take median over mean? Because of the skewness. And because if we observe only 50% of the data, then also we can have the median survival time. So in Kaplan-Meier, you can have a median survival time, but you cannot have a risk. Again, you can plot a cumulative probability of a Kaplan-Meier only against single variable because it is not adjusted. It is unadjusted. You cannot take, if you can recall, I will show you also in the SPSS, you cannot enter more than one variable. There can be strata, but like we do in the regression, you can have many variables because that's a way for the adjustment of the confounder and the biases. So you can have more than one variable entered in that box. But in Kaplan-Meier, you cannot have. So like this Cox proportional hazard, it assumes that the ratio of this hazard at time T with respect to in one group. So this H1, because generally we compare it across the two group or in randomized control trial, maybe H1 you can take as an intervention and H0 as a control. So you see that the ratio of hazard between the intervention and control group at any time point, it is a constant. This H1T is the hazard in the exposed group at time T, like I was talking in case of a randomized control trial. And this H0T is the hazard in the unexposed group. In this case, you can take H1T and H0T also as a categorical variable, like male and female, maybe the various categories of BMI. So this constant, which we have seen that at various time point, it will be constant. This assumption is known as the proportional hazard assumption. And we need to satisfy this assumption before we can go for this test. Although we have seen a review where they have reviewed 1200 survival analysis article, and they have seen that only 15% of those survival analysis article, they have tested for this Cox proportional hazard assumption. So although it is mentioned in the literature, but we don't do it. So now this is again also known as the Nelson-Allen estimate of the cumulative hazard function. So if this is again same, that H1 at time T and the ratio of H1 and H0, and at a different time, it is a constant. So if the proportional hazard assumption is correct, then the graph of the log of cumulative hazard function in the exposed and unexposed group, this will be parallel. How we can do that, we'll be seeing it shortly. So now we remember we have done this Kaplan-Meier interface in the SPSS, and there I was talking that in the factor, you can have only one factor. So this is one of the limitations, that you cannot check for the other confounder. In case of a survival, maybe if the person already had an attack of cardiovascular disease, CHD in the past, maybe that can act as a confounder, but you cannot check in the Kaplan-Meier curve. So in case of a Kaplan-Meier, we use this log rank test to test that there is a difference between the survival times of different groups. But it does not allow other explanatory variable to be considered. You can have only one explanatory variable. So this Cox regression, it can use multiple predictors. These multiple predictors, like logistic regression, can be continuous or can be categorical. Here it is written binary, but you can take polytomous variable also, which has got more than 2 categories. Then the second, but if I want to understand the effect of multiple independent variables together, then you need to know the Cox Proportional Hazard model. So this Cox Proportional Hazard model, it is also known as the Cox Proportional Regression method, because many times people ask, like, are these two same? So yes, this Cox Proportional Hazard model is also known as the Cox Proportional Regression methods. That's why there is you will see that analysis is very much similar to the logistic regression. The result of logistic regression is usually expressed as odds ratio, whereas the result of Cox Proportional Regression is expressed as the hazard ratio. Otherwise, apart from this time, a factor into play, everything else you will see, if you know the logistic regression, you will not have any difficulty in understanding the Cox Proportional Hazard. The interpretation part is exactly same. Here also we express it as an unadjusted hazard and adjusted hazard. Now there are a few assumptions which we need to check before we apply this Cox Proportional Hazard. So first assumption we have seen that the proportional hazard assumption, this we check by log minus log curve, and the second by the time-dependent covariate. We'll see what are these two. And then the second is, like we have seen with the multicollinearity problem in the linear regression and in the logistic regression also. So if there are more than one independent variable, which is a scale variable, then you need to check this multicollinearity also, which can be checked by the value of standard error and also by the collinear statistics, that is the value of correlation coefficient. So this proportional hazard assumption, this says that the relative hazard over the time that are proportional or that are constant. So like if I say that the risk of dying at a particular point of time in one group is twice that in the other group, then any other time point, whether it is T1, T2, T3, Tn, we can say that the risk is twice only. So in other words, we can say that hazard ratio, it doesn't depend on time. So hazard rate, we have seen now the answer to the question. Like, what is this hazard rate and how come this hazard rate has suddenly come into the picture? So we have explained this in the beginning regarding the episode of event. So we have, while we calculate the risk, we look the entire time as a whole. So if you have to calculate the risk at this time point, you are not going to be worried whether it is high in the early period or in the case of a female and high in the late period in case of a male. So we calculate the risk at the end. But in case of this hazard rate, it is the instantaneous rate. So if you divide this arbitrarily at a small period of time, then you can say that the hazard rate, so Manoranjan is writing if it is not constant, let me check. No, if it is not constant, then we apply a hazard, Cox proportional, but that model is known as the extended Cox proportional hazard. I'll be briefly touching that thing today. So hazard ratio and rate again. So hazard rate is for a single individual, and ratio is when you have in the numerator and denominator, depending on the reference level. So hazard rate is for the single group overall. When you have got more than two group, then in each individual, like if I am explaining the hazard rate in male and hazard rate in female, you will just see what is the difference. Then the ratio between these two, it will be the hazard ratio. Okay, it is exactly same like odds. Remember, we used to calculate odds in one group, odds in the other group, and then we used to express it in the form of odds ratio. Again, in odds ratio also the reference category is very important, because the odds ratio will change if you change the reference category. Like if you have taken 0 and 1, if you are taking 0 as a reference, and if you can recall, we had this long discussion, maybe those of you who are joining this session for the first time, you can see our discussion in the basic course on JAMOVI, and we had a very lengthened discussion on this reference concept in the odds ratio. And here, because time, it is almost the same concept, like you explain, you define, but there the odds calculation of odds was very easy. You just in 2 by 2 table, you used to take A by B. So that we can do manually also in 2 by 2 table. But since this hazard rate, I said that this is a complex mathematical formula, and you cannot calculate hazard rate just by seeing the table, because it involves the calculus part. Deliberately, I have not mentioned any mathematical formula here, because what I think that being medico, because most of us are medicos, and somehow we don't have a very much nag, especially this calculus part. Simple mathematics we can understand, but that it's not needed also, because as a researcher, it's more important for us to check for the assumption, and if that result has come up, how will I interpret, and in what situation should I go for a particular test. So that is more important. That's why deliberately I have not given the formula of hazard rate. But remember, it is some d by dt, we take the calculus into this thing, and we take some exponents of this survival probability, and that's how it is calculated. So this hazard rate, unlike the odds ratio, cannot be calculated manually. So that's how this mathematics, like it is there. And in this case, you can say that event, it is because it's instantaneous. It's not a single point event. So the risk set, which we have defined, that the people who are at risk of development, or the proportion who survived after that time, that keeps changing. That's why and if you divide the hazard rate of one group with the hazard rate of the other, so whatever we take in the denominator, that acts as a reference, like in case of a odds ratio. So I think by these explanation, you understand what is a hazard rate and what is a hazard ratio. So hazard rate is synonym, it's very much like odds, only odds, not odds ratio. And hazard ratio is like odds ratio. So if you take the time component along with odds ratio, it becomes hazard ratio. Similarly, if you take time component, because it's the time changing time, that's why that calculus part is there, then it becomes the hazard rate. So all of you, have you understood this point? What is hazard rate? What is hazard ratio? Hazard rate can be calculated by the survival probability. You have calculated the survival probability, haven't you? In the last 2 classes, I have shown you in the SPSS, in the life table also, how you can multiply at each time point, you calculate the survival probability, and then you multiply that survival probability. Remember? So that is the survival probability that you can calculate from a table. But this hazard rate you cannot calculate. Okay, so any more questions before we go further? Or any more?
Madam, I just need to clarify one thing.
Yes, Dr.
Uh,
Shivaji?
at the beginning of today's session, it was said that hazard ratio is like just you said. Hazard ratio is time dependent odds ratio.
Yes.
But is it only for Cox that this ratio remains constant?
To apply a Cox regression, we check this assumption whether this is similar across each time point or not. If it is not, you cannot apply the normal Cox regression. In that case, you have to apply, there is something known as the extended Cox. Okay.
Okay. That's the limitation of Cox proportional hazard model. But hazard ratio can be time dependent. But in Cox, we are taking that it is constant.
We are taking that the ratio at each time point, it should be nearly constant. We will not say that it should be exactly like we have seen in the different example. And there are ways to check that. I will be coming to that. Because whenever you see that the curve, this log minus log curve, this is crossing. Like remember day before yesterday, you people were saying that why this log rank is significant, because it is crossing and it is touching the two curve. So it is like you can say that whenever it crosses and it becomes like whatever was the upper, it came to lower, and whatever was the lower, it has gone up. So if it is something like that, then you cannot apply this Cox regression, because we will see in log minus log curve, the distance between the two curve, it should be nearly same. It should be parallel rather. It should never cross each other. So if that is there in log minus log curve, that means this assumption is somewhat met. There's another concept of time dependent covariate, and that is only applicable if this assumption is not met, because that says that with time, like in this case, I will give you this example which we have seen. Yes, in this example, so you can see here that the Cox proposed this hazard ratio. This is changing at different point of time. It is not 1.2 here at, sorry. If you see at this time point, it is not same as 1.2. At 9 months also it is not same. Here also it is not same. So what have you seen? That the hazard is also changing and the ratio is also not constant. In that case, what should I do? Now, Dr. Shivaji, can you answer this? What option do I have?
The extended variant of Cox.
Yes.
Okay,
in that case, I cannot go for Cox proportional hazard. There are varieties of Cox regression. Right now, we are discussing Cox proportional hazard. There is a time-dependent covariate Cox model. Okay, that option is there in SPSS, but not in JAMOVI. I will be discussing that and I'll be showing that time-dependent also. In case you need it for your analysis, you can apply that. Okay, but the entire focus is on the Cox proportional hazard. That's why you need to check the this proportional hazard assumption. Did you get it? All of you?
Yes, ma'am. Yes, thank you.
Apart from Dr. Shivaji, any other person who is having any confusion, then please clarify it right now, because then you will be able to understand when you go to the breakout room, or you will have to interpret why this Cox proportional. So Manoranjan is writing yes. So whenever you see that this is changing, this ratio is changing with time, and that's why you need to check this with each variable. We'll discuss this, that what variable to be put into the model. How will you decide for that? So that also, apart from the clinical judgment, you will check for this proportional hazard assumption. And if the proportional hazard assumption is not met, you cannot put that variable into the model. Okay. Or if you want to put that model, put that variable into the model, go for the extended Cox. Is it okay? I will again repeat this concept. I will repeat this twice, thrice, So there should not be any ambiguity while you attempt. And we are trying to keep the things very simple. That's why you will not see any mathematical formula in our presentations, because we ourselves are not very much comfortable with very, those complicated mathematical jargon. That's why maybe we are trying to know what we can say, like keep things a little simpler for the understanding of everyone. But I don't know whether you have understood it or not, because by making things simpler, I don't want that you people should not understand. So let me check the chat box. So I can see Sunanya, Manoranjan, Amir, yes. Radhika also yes. Okay. Then I am taking these people as a proxy for the whole group that you have understood. Maybe if you have not understood, if I will repeat it twice, thrice, then you will, it will be there in your brain. So, yes. So proportional hazard, like I have written here, time-dependent covariate. Proportional hazard assumption, if it is not met, that means the hazard ratio is changing with time. And that ratio is not constant. And there's a way to check it. So there is a graphical way, which we check by log minus log curve. And there is a time-dependent covariate. And second is the multicollinearity. And you all know, because you have done it in the linear regression, the logistic regression. Whenever we have more than one independent variable, which is scale variable or a continuous variable, we always check its multicollinearity. So this I have done, and this you can see by these three, you can say that it is not constant. We can see that this is hazard rate, but this is not constant. So this is simple. I have don't just consider that I have taken the time into the consideration. So I have started this is the first week, this first column. If I explain this table, this first column is for the time period. So it is the first week, second week, and third week. This second column is for the treatment arm. So you can see there is an experiment and there is a control arm. Number of patients at risk, you can see we have started with the 100. So this is A is the number of patients who are at risk. This is the number of people who died during the time period. So the 3 people died in the experimental arm and the 4 people died during the control arm. And these are the number of patients drop out. This is sensory. So now the rate of, now again here, this rate is, you just take it rate as a proxy for hazard rate. Actually, it is not the hazard rate, because I said that hazard rate we calculate it with the calculus formula. So, but just take this as a proxy of hazard rate. So rate of dying, what will be the rate of dying in this case, first case? So in this case, you can see there are total 3 deaths. So the rate of dying will be 3 by 100 in the experimental group. And in the control group, it will be the 4 by 100. So the ratio, what will be the ratio of these two? So just consider this. This is, we have calculated on the basis of the hazard rate. And that, and this is censored. So this is 0.03 and this is 0.04. And if you see the proportion of patients dying in the experiment arm as compared to the control arm, then you can see that this is 0.75. Similarly, if I start, so if there are 3 people and there were 0 dropped out. So again, if I have to reduce this 3 from this 100, so it is 97. And in control arm, it will be 96 because there are 4 people here. So it will be like 97 and 96, number of people who are at risk. Now the number of people who died. So 6 died in the experimental arm and 8 died in the control arm. And there was a 3 dropout during the period and there was a 1 dropout in the control. So number of people, it will be 97 minus 6 plus 3. In this case, so it will be 88 here. And in this case, if you see this 8 plus 1, we'll deduct it from 96. So it will be 87. Now, if I want to know the risk in this case, it will be 6 by 97. It will be 0.06. And in control arm, it will be 8 by 96, which is 0.08. So this is again 0.06 by 0.08. And again, I am taking reference here as a experiment. So it is 0.74. Similarly, if I calculate risk here, it will be 0.10 and 0.14, and the ratio will be 0.71. So you can see it is most or less the similar example which I have given earlier. So we can say that all the three, it is near what assuming the proportion hazard concept, because it is nearly constant. And I said that you just take this as a hazard rate, not as a rate which is here. So if the experiment arm is being taken as a reference, then shouldn't be, yes, you can do that. You can do that. You can do the other way around. You can do this 0.04 and 0.6. So you explain this, that the death is less. That's why this control is kept as a, what we can say. We have kept this control as a reference. So what did you write through? If the experiment arm is being taken as reference. No. I said it wrong way. It's not the experiment. It is the control which we have taken. That's why control is in the denominator. You can see here. And that's why the risk of death is less in the experiment arm. Maybe if I'm trying to see some effect of the treatment. So I'm sorry. The reference here is the control, not the experiment. And usually we express that because we take the control as a reference and we want to express the hazard ratio in the experiment arm. So this hazard ratio is basically we use this in time to event analysis, and we have seen that it is a ratio of hazard rate. It is the ratio of 2 hazard rate. Hazard rate, it is calculated using a calculus formula from the cumulative survival. And cumulative survival, you know, that people who could survive past that time t, that is 1 minus hazard. But again, that 1 minus hazard is not the hazard rate. That is a simple hazard. So there are 3 terms. There is a hazard, there is a hazard rate, and there is a hazard ratio. So like if I say that hazard of a person in a particular day is 2%, that means if I have 10 people, 0.2 will, or if I have 100 people, 2 people has got that risk. So that is a plain hazard. So plain hazard is the, when you do 1 minus that hazard, you calculate the probability. So there are 3 different terms: hazard, hazard rate, hazard ratio. Hazard is simply the failure. If you and then you calculate the probability of survival. So from that survival probability, using a mathematical calculus formula, the hazard rate is calculated. And when you take the ratio of those two, we define that as a hazard ratio. So hazard ratio is the hazard in the treatment arm, and in the reference you take in the hazard in the control arm. And this hazard rate is actually here, it is hazards means hazard rate. And it is the instantaneous event rate. So it is a probability that an individual at time t has an event at that time. So you assume that the assumption that the event free up till time t, that person was free from that event. So now likewise we have this calculation of odds ratio, and we explain how we interpret the odds ratio. Similarly, we calculate the hazard ratio. So this relative risk or odds ratio we calculate at the end of the study. But hazard rate, like we have discussed, it takes both the number of events and the time of each event across the entire study period. So it is same like if it is less than 1, more than 1 and 1. You know, like if it is 0.5, then at any particular time, half as many of patients in the treatment group are experiencing an event compared to the control group. If the HR is 1, then we can say at any particular time, event rates are same in both the group. And if it is 2, we can say that any particular time, twice as many patients in the treatment arm are experiencing an event as compared to the control group. So coming to a little bit of mathematics. So in the linear regression, remember we explained this dependent variable as a beta 0, which is a constant, plus beta 1 x1, beta 2 x2, and beta n x1. This is the formula for a linear regression. In this case, instead of this plus, it is the multiplication. So if you see the modeling, because it is modeled like this. So the probability of an event, it is called the hazard or hazard rate, and it is modeled at ht is equal to at time t multiplied by, here it is the exponent. So this is the exponent, not the simple one. And you will see in the table, like in logistic regression also we calculate exponent, we will see that. So it is the exponent of these expression. So if you divide both the sides by h0t, then it will be like h0 ht by h0. And if you take log, because if you want to remove this exponent, it should be a log. If you take the log, this exponent is removed. So you take natural log both sides. So this is log ht by h0, which is known as the hazard ratio. And this is the like beta 1, beta 2, this like this. So you can see here, interpretation again, we'll see this, but again you can express this as HR minus 1 is the percentage change in the hazard when the covariate increases by 1 unit. If it is a continuous variable, or if it is a categorical, you can say taking the reference category. And this sign will convey the direction of increase or decrease. So again, this is one example. You can see this is one curve, and you can see with the time, this hazard. So survival, you have seen that survival curve comes down, that Kaplan-Meier. So it is like a stepwise and it goes down, but this hazard, it goes up, this hazard rate. So if you see this, if I say that the hazard ratio, it is 0.64, and there are two groups. So this dash is the we can say that this is the atorva, this is the traditional treatment. This solid line is for the atorvastatin group, and this is the dash is for the placebo. And if you see X and Y, this is in the years, and this is the cumulative incidence, which is the hazard in this case. So we can say that the atorvastatin group has 36% less hazard of experiencing the event at any given point of time. And you can see this curve is somewhat parallel. It will not be exactly parallel, but if you see the distance between these two curves, they're never going to meet. So they will be like almost parallel. So by seeing such type of curve, you can say that the proportional hazard assumption is met. And we have seen that we do like HR minus 1. So it will be like 0.64 minus 1, which is this 36%. But again, it comes with a negative sign. So we'll say that the group, atorvastatin group, has less chance of 36% less chance of experiencing hazard at any given point of time. So this was the proportional hazard. We'll see in the SPSS also. I'm just telling you the theoretical. I have not still come to the data set and how we actually do in the data set. Now, there is something known as the multicollinearity between the independent continuous variable. So to check for the multicollinearity, the value of the standard error, which is there in the table, it should be 0.00125. And there is a Wald statistics also, which is not, I have just written for your information, that Wald statistics is the square of this beta divided by standard error. So now let's see it in the command. So first I'll be telling you this in SPSS. Now again, like other cases here also, if you combine both these two software, it will be easy for you, because the adjusted and unadjusted hazard, that comes that good table comes over JAMOVI. But again, proportional hazard assumption, we could not check it on the. So can we have a 2-minute break? So are we all ready? Ready to go? Okay. So you have asked one question, what do we mean by HR minus 1 or 1 minus HR? So basically it is, we do it like 100 because that is in the form of fraction. So we do it like 100, like if you see the formula, which I have just shown, it is basically 100 multiplied by HR minus 1. That is just to convert this fraction into percentage. So it tells us like this much, just a way of interpretation that we did in the logistic regression. So it changes it tells the percentage change in the hazard when the covariate increases by 1 unit. I'll be explaining this in more detail when we'll actually see the table. So like if I say the hazard rate, that is 0.74. In this case, if you see this HR is 0.64. So if I do like 100 in the bracket multiplied by HR minus 1. So what will be the value of this 0.64 minus 1?
0.36.
0.36, and it will be minus 0.36. Right. And you have to multiply it by 100 because I have written because it's in the fraction and you have to convert it into percentage. So it is 36%, but it is with a minus sign. And I've said that this hazard ratio, it takes the control as a reference and treatment group in the numerator. So a minus sign that suggests that the hazard is 36% less in the treatment group as compared to the control group. Minus is protective. Yes, you can say minus like minus is protective. Yes, because the value is also less, na 0.64. So 1, we say that like odds ratio, we say that it is protective. But if you want to write it in a unit, like if you want to say that the treatment group has got 0.64 times hazard as compared to control group, you can express that way also. So either it can be expressed as a ratio or it can be expressed as a percentage. If you want to express it as a percentage, then that formula of 100 in the bracket, HR minus 1 comes into the play. If you don't want to use that formula, and if you want to go by the simple ratio, which is here, like 0.64, I may say that the hazard is 0.64 times in the treatment group as compared to the control group or the placebo group. Is it okay? So yes. Okay, so Shivaji is now leading the discussion. So any more questions from any other person? Dhruv is writing, when reading articles, what does HR mean? Hazard rate or hazard ratio? It is the ratio. We never express any result at odds. Remember, in odds ratio, we never express any result as odds. Similarly, we never express, because this survival analysis, it is always done either in a cohort, prospective cohort, or in a randomized control trial. Remember our first class. So you always have a two group. Either you have got a comparison group and a high risk group, or you have got a treatment group and a control group. So single group hazard has got no meaning. What is a reference? So that's why wherever you read this HR, it is the ratio. Okay, Dhruv is okay. Any other question before we go to the seeing actually how it is done on SPSS? So if not, so this is the question. So in a study, the researcher followed 192 cases. Again, this is the same problem which we have been discussing for the last 2 sessions. 192 cases of first MI attack over 7 years. Second attack of MI, it was as an outcome was observed during this period. 0 was censored and first was a second attack. 70 patients had second attack of MI over this period. The researcher wishes to estimate the hazard of second heart attack for age, gender, BMI, and smoking. And I have to see that for in all these, this thing, what is the hazard rate for second heart attack? And further, I have to calculate the survival plot. So I'll come to this SPSS again. I will be first showing you with SPSS because the assumption checking we could not find in the JAMOVI. And in JAMOVI, there were 2 queries before we ended the session. Then I think Bijit also cracked that and he has posted in the group regarding that changing. Even we could miss that. But thank you, Bijit, for pointing it out. And I'll again show how to change that probably unit of time, which was by default coming in months. So all of you, please remember what was that?
Yes, ma'am. Yes, ma'am.
Okay, so we'll see that, how to do that. Even Naveen got stuck up and then he was refreshing
yes,
and
ma'am.
then it is not coming.
I had to refresh it, ma'am. That's it.
Yes.
Like we forgot to refresh it.
Yes, that's okay. That is there. JAMOVI, many times it happens. So we should not lose patience and, we should try it again. So then it may come. So yes, that was the question. We'll go to this is the same data set. Again, I'll show that these are the variables like age, gender, race, cardiovascular disease, MI order type, BMI category, the smoking status at baseline, and the follow-up duration and follow-up status. So this is the analyze option. So I'll go to analyze, go to survival. And we have seen that it can be checked by 2 ways. First is the log minus log curve. So you click this Cox regression. This interface is very much similar to the logistic regression. So except this, you have to enter the time here. Follow-up time, then this final status, give a value of this event. So 1 is event, continue. In covariate, like let me see the question. So the question was age, gender, BMI, and smoking. So I'll go again. I'll enter this age, gender, BMI, and smoking. That I have entered. Again, I have gone to categorical. I will, like we do in the logistic, you have to define this, like which is the categorical variable. And usually we take the lower category as a reference. But I don't know why this SPSS always takes this last category. So I have clicked this first and press this change. So when you will click this first and press a change, you will see in the bracket this first will appear. This first. If it is appearing, then that means it is taking the first category. So that is there. This, it has not appeared. Okay, this BMI category it is taking as a first. So then I'll go to the continue. Then I'll go to this option of plot. So in option of plot, there is a hazard plot and there is a 1 minus. So you can click this hazard also, but right now I'm checking for the log, sorry, not this 1 minus, rather this log minus log. So it takes this log twice. So right now, maybe I'm checking for gender. So you can have only one variable here. And right now I'm not going for that hazard, this thing beta coefficient or all. So I will click this and I will see like what is the curve. Because I'm now going. So this is you can see log minus log curve for gender, LML. It will write here as LML function. This log minus log function. Here also you will see log minus log. So what can you see here? What is your opinion? Is this assumption met or not met? What is the opinion of the group? Met. Shivaji is writing met. Okay, Pragya is writing met. Manoranjan, Sinduri, all met. So if it is met, then I may keep gender in my adjusted this model. Okay, so I have tested for this gender. Now again, this is adjusted one because you can see here that I have all the variables in that box. Now again, I'll go to analyze, survival, Cox. Again, I'll go to this plot. And instead of this gender, and this log minus log curve is for the categorical variable only. It is not for the continuous. So here I will maybe I can enter this and I'll press this continue and OK. So if I see this for this smoking status, then what is your assumption? Is this met or not met? Proportional hazard. You can see there is almost a parallel line. And again, it is, we cannot say that it should be exactly parallel. We just see that the line should not go blue should not go up and green should not go down. It should be almost parallel. So again, met. So we have decided to keep this smoking also in our model. I'm just writing. Again, I may go and I can try for the other variable. So I'll go to this plot. I'll move this back. I may have this. I'll press continue and press OK. Then you can see here, what is your opinion regarding this BMI category? This is also met. So BMI category is also met. So then I can go ahead with this model, and there's no need for me to go for this time dependent. Like for example, I'll say, so first, so we have multi-collinearity for continuous variable. No, there is only one continuous variable here, that is age. So there is no problem of this multi-collinearity. Usually
no, ma'am, for the assumptions in general cases,
okay,
we take multi-collinearity for continuous variables and log for categorical variables. That's
okay,
those are the only assumptions.
Okay, yes.
Okay, ma'am.
So then we can go with this survival, Cox regression. So till now I have not clicked on the other option. So it will I want this confidence interval, that is a 95% confidence interval. I'll press OK. This save is only for the option if you want to have some data created in your SPSS table. So this I don't need, and categorical I have done. So if I press OK, then this comes. So this gives you the coding also. You can see here that if you have forgotten the coding, in my coding it was 1 and 2, but it has coded it as 0 and 1. So on SPSS by default, it takes whatever comes, it has taken one male as 0 and a female as 1. Again, you can see the coding, it is 1 for normal and it has taken 0 for this thing. So if you are saying this 0, 0 in obese, that means it has taken this obese as a reference, and it will give you the hazard ratio in normal and over. Yes, you are right, Paramita. This wherever this 0 is there, that means it is for the reference. And in this case, if it is smoking baseline, so no smoking is reference, and yes is it will give the hazard. So it is important for you to check these codes because that will help you in writing the interpretation. So you go here, again you see this. So now coming to this log likelihood. So when there is a without any model, the value of this -2 log likelihood, I'm not going into the detail of how this -2 log likelihood is calculated. But if there is a change and if there is a reduction from the previous value, we can say that it is significant. How obese comes first in the reference. So obese, if you want to take underweight, then you have to reverse the coding. Maybe because in our original coding, let me see. So it has taken this obese as a reference. So maybe the higher category, it has given it as a 0 here. Why? I don't know why, but it has given. It's important for you to see these codes. And if
Madam,
you
when you gave that first and last thing, the
okay, maybe
last thing
the
was
second or
mentioned in
first.
PM. Yes,
Okay, okay.
we didn't select the first category.
Yes, I was trying to do that. Okay, okay. Let me do that again. That's why. Yes, you are perfectly right. I can recall that. So let me change that. Okay, yes, very right. Because I also see that change of category was not appearing there. Yes, there it is not coming first. So let me select. Oh, that's why. Oh, so good, na? I was not observant at that. Yes, but if you change, then only the other will change. First, and then change. So yes, now it will not come. So yes, now you can say, thank you, Dr. Shubhaji. You can see here. So now it is 0. Okay, yes, you are right. When I changed that, that was left. And that's why it was taking 3 as a higher. So we may do these mistakes quite often. I mean, we can do it if we are not very observant. And if there is a slight loss of concentration, then that mistake may happen. So again, go back and see what we did. So the lesson learned from this exercise, again, go back and redo the analysis rather than, right now, the Dr. Shivaji was there, he pointed it out. But maybe if you are sitting alone and trying to do something and not able, then you just close everything and just do all the exercise afresh. Then maybe that mistake which I did here, that may be avoided. So you have seen the coding. And then I was discussing this -2 log likelihood. So we discussed this concept in logistic regression also. The reduction in the -2 log likelihood. If the larger amount of reduction in the value is there, the more significant the model will be. So the value, it has decreased from 595 to 565. And if you add this, please add 565 plus this 29.48. Please add all of you. What is the value? 565 plus 61 plus this 29.48. Or I can also. So 5, 6, 5.
595.1.
Plus, thank you, Naveen, 29.48. So it is approximately the same value. Some difference is there because if you take like many points up till decimal, but it is 595. So this chi-square value, which is written here, this tells you the reduction of the chi-square value from the previous log likelihood. And this tells you the significant level. So if this change from the previous -2 log likelihood is significant, that means it says that the model or the variable which you have put in your final Cox proportional regression hazard model, this model is significant. So do you understand this? Have you understood this concept? This model coefficient and the value of this significance and this change from the previous score. So now coming to the variables in the equation. So these are the variables in the equation. So the first variable, this is the coefficient. And this, if you take the exponent of this, it will give you the odds ratio. Okay, so there is a question. Let me see. Model significance. Okay. So Amir, model significance means there can be a case that if this value is like more than 0.05, that means variable which you have taken, that is not able to predict because you are just predicting something. Based on your data, you are predicting the survival or the hazard in the experiment group as compared to the control group. So that prediction which you are doing, that is not significant, the model, because it makes an equation. And on the basis of that, you say that maybe like 5 years or after 6 years or maybe after 10 years. So this model 0, when if you see this beginning block, so this is the case processing summary. And if you come to this beginning block, here it is not taking any variable in the model. So if you don't take any variable in the model, and when you take variable in the model, so it tells you that how your model, whether the variable which you have taken to predict the hazard in the experiment group as compared to the control group, whether that model is significant or not. So ultimately, like in logistic or in linear regression, there is a concept of residual. Remember, you calculate the expected survival and you calculate the observed survival. And that chi-square, which you are seeing here, that is again calculated based on the expected and observed survival. So from this, you are telling the expected survival and how much, but the R square, which you get in the logistic, that doesn't come here. So this tells you that what is the difference between the observed and expected survival. Like we used to do it for the probability in case of a odds ratio or the logistic regression. So this tells you if the model is significant, that means whatever observed, there will be a less difference between your whatever you will predict and whatever is actually observed. So the smaller the difference, more important will be, because these all are prediction models. Remember, these are not accurate. Like, how can you predict after 20 years what is going to happen with this particular group? So these are all predictions. And when you compare that, how good is or how this model fits. So whatever we talk about model fit, that is in regard to the in context with the actual survival. So this -2 log likelihood is like, you can say this is the amount of residual. So lesser this is, the more it will be. So by applying your model, this residual. So do you know what is residual, Amir? No, Dhruv is also okay. So residual means like, okay. So just, okay, so Sunanya is also, she also doesn't know. So and that's just to how to make, because then I'll have to, okay, I will give you a hypothetical example. If I want to say, based on some probability, so there are few indicators. I have taken like number of hours a person study, gender of a person, and the stress level, maybe any stress level which I can measure, and then probability of cracking NEET or not cracking NEET. Okay, if I want to see, if I have a data of 1,000 students and I have taken 3 variables: gender of the individual, number of hours that person used to study every day, and the stress level of that person. Okay, and whether she has taken coaching or not. So do you understand what I'm talking? All of you who don't know the concept of residual, do you understand this? So Dhruv, everyone is saying yes. Now on the basis of that, I have predicted something, that a person who is a female who used to study for 12 hours, if you like, there is a formula. So if you put that value in that formula, it says whether that person will crack NEET or will not crack NEET. Okay, so it gives you the value between 0 and 1. But that is your predicted one. But there can be a case where you have predicted that she will crack and she could not. Then what will you say? That your model is not correct, right? So the difference between your prediction and the actual, that is the difference. So whatever with that equation, you predict the value and what is the actual value. If you are predicting marks, so maybe I can talk in terms of a linear regression. So if I'm predicting that the first year students, maybe the same variable, the gender, the number of hours, so she will secure maybe 90 or maybe 100 or maybe 80. So the difference between her actual marks getting and my predicted one, the difference between these two is known as residual. Do you understand this? Okay, Pragya, that again, that's a different concept, standardized and unstandardized. That is a little, then this will go entirely to the discussion of residual. So that we will address, but that's how you can understand, because we all are medical students. So all these models, they are for the prediction. And the lesser the difference between the observed and predicted, more accurate the model is. More difference between observed and predicted, then it is not accurate. We say now, whenever you go to some person who sees the your heart and say ki aapke, you will get this in future. If something of that, so that is prediction. Although he's doing it non-scientifically, there's no scientific basis. But if someone is doing prediction based on these mathematical concept modeling, and when there is a less difference between the lesser the difference between the predicted and actual, the more significant model is. Okay. So I hope now you got it. So this -2 log likelihood, this is actually, you can take it as a proxy indicator of residual. So because it has, with the application of model, it has decreased this residual by 29.488. That means now your model is accurate and its value is also significant. We don't go by the amount of residual because we don't know that this value is significant or not. But if this tells you that this is significant, then we say that whatever variable we have kept, that is, those variables are carrying an important role in our model prediction. Okay. So then I'll go to this variable in equation. So these are the variables, and you know now what is coding 1 and 2. And if it is giving you gender, then it gives you with respect to female. So it is taking, because female, if I go down, up, sorry. You can take female is coded as 1, sorry. So let me write it somewhere because I also forget. So female is 1. Here the male is reference. And here the normal is reference. So you may write somewhere, because again we have to come down. In JAMOVI, it gives you with name, so there is no problem. But in SPSS, you have to see the coding. And smoking is, no smoking is the reference. So male gender, no smoking, and the normal BMI. That is the reference. Now coming to the interpretation. So now this table is the most important table. And this table we give in our manuscript. This is the adjusted hazard ratio. I'll tell you how to calculate unadjusted also. So when you have only single variable, that is the unadjusted hazards ratio, because you have not adjusted for the other confounder. And you know what is a confounder? A confounder is a variable in the presence of which the effect gets either overshadowed or overexpressed. Like in this case, if I say that smoking can be a confounder, for gender, if I say that the survival was more in female, and if the females are non-smoker, because generally females are non-smoker as compared to men, then that smoking can be a confounder. So if you don't adjust for smoking, then your hazard ratio will not be a true reflection. So we adjust it for the known confounders. And if you don't know about a confounder, you can keep on putting the variable and seeing whether the hazard ratio is changing or not. I'll show you. So just to explain first, that is the age. So I'm explaining it with the age. So if the value of this, and you see the significant also. So how many variables, who has got a significant level? So age, gender. In fact, all are significant except this smoking. Smoking is not significant because its significant value is 0.179. And you can see this BMI category 1 also. It is also not significant. So it is only this significance, the overall significance which you are seeing here. That is because of the difference between this 2 and 1. That means the comparison between the obese and normal, because our reference is the normal. So yes. Now what does this mean? 1.37. How I will write that? That with each 1 year increase in age, the odds ratio in the experiment group, sorry, not odds, the hazard ratio in the experiment group will be 1.037 times as compared to the control group. So in case of a continuous variable, we expressed it as 1 year increase or 1 unit increase. In case of a categorical, we take the reference. So like in case of a gender, how will you say that? So male is my reference because male was coded as 0. So I can say that the hazard of experiencing, or the hazard ratio for experiencing the second attack of MI is 2.2 times in female as compared to male, and which is significant because it is 0.005. Similarly, if I have to say for this, because this is significant, I can say that the hazard ratio for obese individual for having second attack of MI is 2.86 times as compared to the normal, because normal is the reference category. So you have to comment only on the significant one. The non-significant, because it is not significant, so you can leave it as such. So this is the interpretation. And this LML function, we have seen how we plot it like for every variable to see this. So have you understood all these concepts? Then I'll tell you how to do it in JAMOVI. Or do you want me to repeat? What is the time?
Madam, for logistic regression, what we usually do is we do univariate logistic regression for individual variables. So is it necessary over here that we do for individual variables?
Yes. That's why I've just not told you deliberately that because in JAMOVI, it gives you both the value, unadjusted as well as adjusted. But if you don't want to use JAMOVI, then you can simply come here, survival, Cox, and you move everything back to this window and do it one by one. So press OK. Then you will have the unadjusted hazard.
So we only take those variables whose
So it is 1.024. Yes, you take one by one. Again, go to survival, Cox, you move this, put gender, again OK. See the value of gender. So see the value of gender without unadjusted is 1.79. And if you see the adjusted one, it is the 2.2.
And so is it that we only take those variables that show significance in univariate analysis into the model?
Yes, that you can do that. But again, we say that many time a clinician say that it is important for me, although it is not coming significant, but it is important for me. So in that case, you can have either a statistical significance or a
Still
clinical
in
significance.
logistic regression also, like we can take up to 0.2 p-value.
Yes, yes, yes. Cutoff, you can decide that it is not necessary that it should be up till 0.05. You can take it up till 0.2 also.
Yes. So there has to be a cutoff. We cannot take every other variable other
No,
than
no,
when it's
point two,
clinical
point two.
significant. Yes.
Point two. If, yes, no, we cannot say that. There are many times when your sample size is less. I'll tell you the reason. And you are taking many variables as a predictor variable, right? In that case,
And still researcher would be somewhat sure that even it is not
yes,
statistically significant, clinical significance can be taken as a
Yes,
basis for
clinical
it.
significance and statistical significance. These are the two
yes,
factors you
yes.
can take.
It cannot be decided only on the basis of statistical. Because there may be a case, I said now that if you are taking 10 predictor variable and the sample size is very less, like maybe like 30, 40 or maybe 60, 70, in that case, it will not be significant.
Yes,
Then you
yes.
advise the individual to take some more cases so that then it will become significant. If he is very much sure, and that we have experienced during COVID, that there were many like interleukin-6. Initially, when it was less sample, it was not coming as a significant predictor of mortality. But when the sample size, it was more, like it became significant.
Yes.
Okay, so I think there was few questions. Let me see the chat box.
Does that sample size cutoff, like in LR, we used to take per predictor variable of 15 at least, we should have a sample size. So does
Outcome.
that apply in survival analysis?
Yes. Outcome. We don't say 15 sample, 15
Like
outcome. Yes. So now coming to this. So this we have seen. So I just wanted to show you that unadjusted odds was 1 point something and adjusted is 2.2 here. And if you see the unadjusted where I took only gender, then it was 1.793. Okay. Again, we'll see in JAMOVI, it is very easy because it gives you both the thing in the single table. So this, have you understood up till this point? Then I'll go to JAMOVI and we'll see. I am not getting any yes or no in the response. Amia is writing yes. Okay, then I'll take your response, Amia. Okay, now Muhammad Antakhab is also writing yes. Okay, yes. So many yes now. So I'll go to the JAMOVI now. So JAMOVI in this case, initially we have used this, for Kaplan-Meier, we have used this univariate. But here we have to use this multivariable because you need to put more variables. So you click this multivariable, then this window will appear. And this follow-up duration, you move here. Outcome, you have to move here. Select this. Here there are two different windows for the continuous and categorical. In SPSS, you need to give the command, like which is categorical. And you used to give the reference value also. This JAMOVI takes the lower category as a reference by default. So I'll move all these categorical. So no, I have to move only gender, the BMI, gender, BMI, and the smoking to this explanatory variable and age to the continuous variable. And in the advanced elapsed time that day we were seeing, if you change this months into days, this changes the axis, which we were not able to do it that day. So this is the option type in output. You can change that. I'm just keeping by default now months. So again, I will close this window and I'll go to this hazard regression plot. So you can have this hazard regression plot. And this adjusted survival, I'm not going plot, you can see change. So if you see this is the table you can see here. So it gives you you can see univariable and multivariable. So it gives you the unadjusted hazard with 95% confidence interval and p-value, and adjusted hazard also. So you can see like this 2.19, it has increased to 2.87. This is also increased, but this is not significant. This is significant. The smoking is also, you can see that it was significant initially. If you see this is a very interesting. In univariate, this was significant. The p-value is 0.003. But in multivariate variable, when you have put all other variable, this has become insignificant. So that's the impact of having adjusted hazard ratio. And age, again, the same thing you can see here. Age is again significant both in univariable as well as multivariable. So this is the plot. You can have this plot, and here you will see that it gives you like male and female. So if it is writing here in front of female, that means it tells you that it is giving you the hazard ratio in female. And if nothing is written in front of male, that means it is taking male as a reference value. Similarly, if nothing is written in front of this smoking, that means it is taking no smoking as baseline. Is it okay to all of you? Have you understood? The interface is just like, but you cannot check assumption here. That's why it's better if you use both or you use only SPSS, because assumption checking, they have not, or I don't know, because we tried to explore, but we could not explore in JAMOVI, this assumption checking. And this hazard, this is one beautiful plot which comes, and you will see like these days, many articles, they report this diagram as adjusted. This is the adjusted hazard. You can see this. So it is for the age, it is for the smoking, this is for the obesity, and this is for the gender. So this picture you can paste it instead of table. If you don't want to give this table, you can give this picture also. Like I'll show you few articles. We have, I was going through because I wanted to show you up. It was where vitamin D level. Dr. Shamshad, can you help me in locating that article where that plot was there? We discussed albumin. No, albumin was, it was not plot, it was a table.
Plot.
Okay, let me see. This is the adjusted and unadjusted. Or NMJ, vitamin D, impact of medication. I'll show, maybe I thought that I'll show. Oh yes, can you see this? I'll enlarge this. So he has not given any table, rather he has just given this adjusted hazard ratio. Can you see this? This graph. This graph. So this graph is only the all effect, like 0 versus 1 medication, 3 medications, aspirin discontinuation. So the outcome here was the mortality. And they have shown that all these hazard ratio, because if you can remember, this is the line of 1. And all the variable values, either towards the right side or towards the left side, will be significant. So if it is towards the right side, then you can see all these are significant, and they have shown it only for the significance. So they have written like they all the variables which was taken in the adjust this Cox proportional hazard, that was significant.
Ma'am, so is it that no medication is safer than medication? It appears to be like that.
No, 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 no. Don't go by that. That I have not gone into the detail of that. No versus any medication, that we'll have to see what is the reference. Maybe that reference will be the outcome. They have what reference they have taken, that I need to check with the exact this thing, because this article we'll share with you. You can go through that. I was just checking how they various article that used to publish the result. So maybe we can, this is the impact of medical therapy discontinuation. So this probably, this outcome which you are seeing, that is regarding the 0 discontinuation versus 1 medication discontinuation. Okay. So
Yes,
a person
yes.
who has not discontinued with person who has discontinued 1. That's what I am thinking from the title. It cannot be like, if you discontinue, there will be no mortality.
Yes.
So for that, I think we need to see. I have not gone into the, that's why I was just checking the how the result is presented in the various articles these days. So how to get these type of plot. So that's what I was telling you. See, you have you got this type of curve here also. You will do it in the breakout room. Can you see this? This is exactly similar what you have seen there. Where is Amir?
Madam, here we have 4 variables, four independent variables, and
Yes.
these will have 4 independent survival plots as per Kaplan-Meier.
That
So
you
if
can, yes. Well, that you have to do draw, because Kaplan-Meier cannot be done for together. That you have to do it separately.
So if we have to report both Kaplan-Meier and Cox, we have to report the 4 survival plots as well as this odds ratio.
Depending on the manuscript, how many figures do they allow? How many tables do they allow? So obviously you give the most important one. So if they are allowing, like, whenever we submit the manuscript, they say that there should not be more than 6 tables, more than 4 figures. So depending on that, if they are saying that you cannot have, and you have some more important this thing to show, then you can present that in the
supplementary tables can be given.
Yes. Those can be done. That is again the entirely the requirement of the journal, how they take it.
Yes, ma'am. Okay.
So yes, there was, I think, one more question. How do you remove the reference spot from the graph? Acha, ye to I have no idea. This is there. Because this graph, he's saying like, it is giving you BMI like normal underweight obese, na? He only wants it should not give, like we were showing that article. He wanted to have a picture like this. So what you can do, I'll tell you what you can do. You can go and you can try some on PowerPoint. I have seen people editing that in PowerPoint. So you can hide that and take a snip. Like, you can copy this and you can paste it in the PowerPoint. And in the PowerPoint, you can use, there are options. In that slide, if you paste it, you can like hide few of the thing by these, there are many design and insert, and you can put new box. Again, save it in the form of some JPEG image, or there are PNG, many type of image, and then you can do that. So you will have to do this editing in the PowerPoint. Not, you cannot, because it doesn't give you any access or anything, or this removal. Or maybe if somebody else knows, then they can let us know, because I tried, but we could not do it.
Photoshop is a good tool. Anything can be done.
So you can use the Photoshop. Okay. Thank you, Dr. Shibaji. So before we go to the breakout room, I just want to touch the concept of time-dependent covariate. Because in this case, yes?
Ma'am, how to change the reference?
How to?
In JAMOVI. Change the reference in JAMOVI.
In this case here, in there, it was the option in the logistic. But in this case, you cannot change the reference. Then if you want to change the reference, you need to change the code. There was an option in ordinal and multinomial, if you can recall. But we could not find changing the option here, the reference category. There is no this thing. There's only change of reference of this. The drop down comes only this. Okay, but if you see the logistic, it comes. So we cannot change. If you want to change, you have to go to this variable, click the variable gender, and it is 1 and 0. So put it reverse. Okay. Any other question? Before I go to this concept of time dependent. So what I understand is that if my model is significant, then I can be more confident that okay, I'm not able to see the full this thing. Where is the, no, I cannot see. Wait. Where is? let me see. I'll see it on my thing. So what I understand is that if my model is significant, then I can be more confident that my predictions are true. So yes, it will not be exactly, but you will be like, that's how you get the value of R square, which is not here. So that tells you how much confident you can be, like variation in one variable gives you the change. So if it is 0, that means yes, you are very much, that residual is less and you are very much near to the prediction. True. You can say that.
Is there something like R square over here? Where
No,
we can...
no, there is no option of R square here. And can you explain adjusted survival curve? So adjusted survival curve, this option comes. Okay, this will open a new one. I'll just click. If you double click this window, the previous operations that will become. So adjusted like overall survival curve. If you want to click, I have not seen its use. First thing is like you can only enter categorical variable here. So maybe if I click the gender here and then see how is the hazard regression. So this is the adjusted survival curve. So this will be, can you recall what was the unadjusted one? If you want okay, I'll just show you. So this will gives you the adjusted survival curve for each variable. Okay, just a sec. Let me see why it is not coming. So maybe I can 2500 because that was the days. Time interval. Maybe 365. Why this risk table is not coming? If it is showing even the 95% confidence interval, it is not coming. Although the option is there. So maybe this is the adjusted survival curve, these two options. But if I uncheck that, so this is the one. And if you see that from the Kaplan-Meier, how that graph, so you can see the female, they have got the less survival as compared to the male. And if you go to the univariate, and there you plot.
Madam, here is a Kaplan-Meier option available in Cox as well. I just saw it.
But that will be adjusted. That won't be unadjusted.
So which should be reported, the adjusted plot or the unadjusted plot?
Obviously, the adjusted. If you are using this thing, I just want to show you the difference between the adjusted and unadjusted. That's why I have clicked this option. So the graph, the appearance of the graph will change. So I've clicked this status here, 1, and then maybe gender. And if you see the plot, survival plot. So this is like this, where we have changed the axis, then the appearance improved. And I will do it to 2500. And here I will do the 3, 6, 5. And there you can see this was. But if you see the adjusted for gender, it is like this. So again, if you want to have a survival for, like, I will again go back to this operation instead of gender. If you want to have this with the BMI category, you can click this. You can click this Kaplan-Meier also. But I think what Kaplan-Meier will give in this case? No, it is not giving. Let me see. Just a sec. Just a sec. No. Kaplan-Meier, okay, it allows for maximum of 2 explanatory. So I'll have to shift this and this. So please use explanatory variable used to build the multivariable model. Okay, okay. So let me again shift this BMI category and this age, smoking, this back. And if I come down here, then what about this? Let me see this. Now this has disappeared. So this you can see adjusted survival curve for the BMI category. This is normal, and there are 3 lines. But these 2 lines are, like, you can see they are merged into single because of they were not significant. We have seen that. So this was that. If you go up, you can see there are many lines. If you see the Kaplan-Meier, it gives you the 1, 2, 3, 4, 5. And risk table will appear here for this Kaplan-Meier. So it is for the Kaplan-Meier. So it makes the graph very complicated. This you can see here. So it gives you the gender, male, and in male, it will give you for all the 3 category, and it will give you the in female all the 3 categories. And then there will be 6 graph. So this will be the Kaplan-Meier. And this can be done only for 2 variable. 2 variable in this case. That's JAMOVI was giving us the hint that you cannot have more than 2 variable. Any other question? Okay, so then we can, is there something corresponding to multicollinearity of covariate, which needs to be tested in Cox regression? So I told now that this. Okay, that value of standard error. So if I go to, just a sec, that SPSS. And if you see this table, where there were, yes. So what value we fixed? So the value of standard error was 0.00125. So it is in between these, so there is no problem of multicollinearity. Okay, but generally we test that if there are more than 1. But again, Dr. Shivaji was telling there are other ways also, but that is problem when you have got more than 1 independent variable which is continuous. Okay, so we can go to the breakout. No, it is 0. Okay, but it is very low. So is it okay now?
Okay.
Amir? Okay.
Yes, ma'am.
Okay, thank you, Amir. So there was a question from Dr. Shivaji that for median survival, but for median survival, you need to put that KM, that unadjusted KM, because you will not get it here in in Cox. Cox is basically for the hazard, and that's the name is Cox Proportional Hazard Regression Model. So it gives you the hazard ratio, but it doesn't give you the median survival time. For median survival time, you need to put separate categorical variable, and then it will give you the median survival time with a significant or insignificant log rank test, or depending on choice of your test, whichever on which part of the curve you want to focus. So that is the one. So now
So median survival time is unadjusted,
unadjusted.
and hazard is adjusted.
Hazard can also be unadjusted. It can be adjusted also.
Yes, but if you are doing Cox proportional hazard model, it's better to give adjusted values.
Yes, you have seen now how the adjusted becomes, the value becomes more or less.
Yes.
Smoking, it was significant, it became non-significant. The odds this hazard ratio of age, it has increased. So gender, not age. So that can be there, and that's how you can discuss those things in your result section and in discussion also. So any other query in breakout room? Could you do it, all of you? Although there are a number of participants are less because many of the participants, they had to leave because of some other prior commitment. But those of you who are here, could you do it in the respective breakout rooms? Practice the command. So you can again keep on doing that. And this feedback form and assignment, that will be shared to you and it will be updated in the WhatsApp group. The date we are not right now telling you, because maybe by Sunday, maybe by Monday, but we'll definitely update you regarding the, there will be a feedback form and the assignment. So it will be a 10 questions based, we cannot say that it is a test, but it is a MCQ, which will be like a data file. There will be a data file which will be shared to you, and the answers are in the form of MCQ, and you have to like put the remark or the select one most appropriate option, and then after that the certificate will be generated automatically once you have attempted that. And this assignment, you all of you please submit it in one file, convert it into the PDF and upload it, and we will check and we will revert back to you regarding how you have written the interpretation. Before, I just want to show you, because that I think we missed, regarding how do we write it. So here you can see this is the crude and adjusted hazard ratio. And if you go down, this is the write-up that a multivariable Cox regression was performed to estimate the hazard ratio. The assumption of proportional hazard was met by the visual inspection of log minus log plot. Multi-collinearity, again, I have written the correlation matrix, but you can write the standard error. The model was run with age, gender, BM, and smoking. The 1 year increase in age increased the hazard of death by 1 point. We have to write the second attack of MI. It was not death. So I am changing it. It is the second attack of MI. And hazard of second attack of MI. So I'll just copy this and I'll paste it here. In female, it is itna times higher. There, though in univariable hazard of death, hazard of this was 1.8 times in smoker, but in multivariable, it's become insignificant. It is due to the fact that the proportion of smoker in female was significantly high, and this you can check with the descriptive. And because before you have performed these analysis, definitely you are going to give some baseline characteristics between these categories, like proportion of male, female, what is the descriptive proportion of all these variables in each gender. So it is due to the fact that the smokers in female are significantly high, and this led to the increased hazard ratio of female in multivariable. Overall survival plot across gender showed cumulative survival decrease faster in females than males. So that's how you can write the interpretation. That's just a template. You can see more papers. We have shared the articles with you, and then you can see that. So if we are done, then we, anything which you may ask from your side. So can you please tell how? Okay. I was about to tell that, but I was waiting if someone is interested, then I may show it, time dependent. In JAMOVI, this option is not there, but in SPSS definitely. So see, like if I see that you can straight away go to this analyze survival. You can see the fourth option. So we have used till now life table, Kaplan-Meier and Cox. Go with the time dependent. So if you click this, there is a appearance of a new variable time dash. You enter this variable here and then click on this model. So now if you click on this model, this will be exactly the same. So here we perform hierarchical regression. So I will put this follow-up duration here, final status here. Event, I have to define it like 1. Continue. Then I have to put this age, gender, this smoking, BMI. Before that, there is a BMI, this smoking. And if I am assuming that, there could be some time-dependent interaction between this smoking, if I can take that, then I will go to the next. So the variable which you want to test whether there is any proportional hazard, this thing is there or not, you can do it like time-dependent covariate. Click that, press shift, and maybe you can click gender. So you have to select both these two together by pressing your control. Here you can see this. This is for the, this is this one. So you have to click that after selecting this. So click that, this will go here. Again, you can click this with any other variable, like maybe you can do it with the smoking, and then press here. You go to the categorical like we have done previously. So move to this BMI category, gender, smoking, like the way we have did it for the Cox regression. And then you select all these three, because in the previous time I did one mistake that was not selected. I have clicked this first and then press this change. So now all these reference category, it has changed. Now I have pressed continue. I'll go to the option, click the CI for 95% interval, continue. So I have used this next and previous. So, okay. So when you click this, now it will give you the 2 model. So it give you the beginning block. Again, it is the same -2 log likelihood which we have done. And this gives you only first the first variable, because we have used a block. So it gives you the values which you can see here, exponent at 95% confidence interval and the significance level. And if you go down, it gives you the value of the all these variable along with these 2 time-dependent covariate. So if you see the significance level, what you have to see in this time-dependent covariate of gender and smoking, the p-value. If the p-value is more than 0.05, that means this doesn't change with the time. This variable is not a time-dependent, and you can be sure that the proportional hazard assumption is met. And then again, you can report, because if you see this, in this case, but if you see the exponent, the value of exponent are different. In this case, if you see this, it is 4.027. It has increased. Even if you see the BMI, it has also changed. So you will find it, although in our case, this is more applicable when there is a proportional hazard assumption, it was not met. So to use this model, ideally this interaction term, this should be significant. Then we will use this equation rather than the simple Cox regression. Is it okay, Mavia? Okay.
Okay, ma'am.
Okay. So if that is okay, then I may stop sharing my screen, and
I
I had a question on the first day regarding probability density and probability mass function.
Yes. We could try to locate that, Dr. Shivaji, but I could not. I'm sorry. I tried to see what is the importance of that probability density. Maybe I was finding some mathematical this thing. You give us some more time. Maybe then I'll try to find out, and maybe we can update in the group.
Okay, ma'am.
Till now, I could not. I'm so sorry.
No, it's okay, fine. Thank you.
Like we could not find enough time also to look because of the, all of us are busy in so many other activities also. But definitely, I will look into that. We have written all those questions which we could not answer, and then we'll see how we can tell you in a simplified way that probability density when I could not do that. I'll see to it, because that is also a hindrance in my mind. That what is that? A simple
Yes,
we are. Okay. Yeah, thank you. Amir, okay, you tried to enroll in the basic of JAMOVI but could not as seats were full. Sure, Amir, we'll try. Until in the meantime, I always say that we'll do, but maybe after this conference, we will try to make some courses. So even if you could not enroll it, at least you can enroll in that basic course of JAMOVI and you can finish that. Then I think you will be able to do all those basic commands of JAMOVI. We'll let you know, Amir, definitely. So any feedback from your side, like how we could have improved? Okay, thank you, Neha.
See you during Ethica.
Yes. We'll meet.
Okay, ma'am. Thank you.
Thank you, Pavia. Thank you, Neha. Thank you, everyone who is giving such appreciation, words of appreciation for us. It is a very meaningful. These words are very meaningful for us. But any feedback which you would like to give to improve the further sessions, although we could not do the more of the discussion on papers, but yes, that is one part which we still could not do it very nicely. So we want to discuss some analytical paper during the session. Maybe we can try in the next time.
Madam, one request. Madam, in future, whether you are doing any workshop in MLR or LR? Is there
Actually, we do the session based on participants' request. So if there is a request for doing the MLR or any other this thing, right now we have got 2 requests pending. One is the meta-analysis. So first we'll do that workshop, meta-analysis, and then we'll come to the other this thing. So
MLR is very essential, sir.
MLR, no, yes.
Okay.
We have noted it down, maybe. Definitely, we have conducted in the past, I think, few, but again, we'll do it.
Okay. Thank you.
Okay. Thank you to everyone. Rutuja, Manoj, let me see the names so that I can thank you. And I can see Shashi. Thank you, Shashi, Shivaji, Anshuman. Then I can see, if I can scroll up and see. Mavia, I have thanked her. Amir, Neha, Shashi, you also want to join meta-analysis. Yes, Shashi, we let you know. We always float first the flyer to the people who were part of any of the workshop. So if our seats are full on those people, then we don't take any other participant. So don't worry, you will come to know all the group wherever. That's why we don't dissolve the group once it is formed. And just to make you people keep updated regarding the upcoming workshop. So definitely you'll come to know. That will take some time. We are planning it maybe in the month of March. But yes.
It will be also very helpful if you can do something on ROC analysis, completely focusing on ROC. So
okay, Dr. Shivaji. I have written down this ROC also. Completely focusing. So maybe 2-day session we can plan in between.
Yes.
Okay, thank you. Thank you to all of you, and it was like a very wonderful experience for us also. And thanks to all our mentors, especially special thanks to Dr. Saket, Dr. Neha, and Dr. Biji, Dr. Arshad, and to Dr. Pallavi. Two more mentors, they could not join this time, but definitely they will be a part of this team in the future. And thanks to the Dr. Venkat, who is our AIIMS Patna team currently, Dr. Venkatesh, Dr. Akanksha, Dr. Naveen, Dr. Purushottam, Dr. Ekta is not there this time, na? Dr. Arun, and if I'm missing out some name, because Dr. Manisha is not there this time. I hope Dr. Haripriya, she's also not there this time. Maybe. Yes, so people, they keep on changing. That's why maybe some has gone, they have gone outside for some other conference. So thank you to all of you for the excellent contribution as a team. Thank you so much. So we may end the meeting from our end. Okay, thank you, Neha. Thank you so much.